This brings us to an incredibly important term that I hope you'll remember from this class. That is interface inheritance. So we'll come to understand it over the rest of this lecture, but basically for now, anytime you use the implements keyword, we're doing what's called interface inheritance. So what I mean by that is all subclasses are said to inherit this interface from their superclass, right? So if any hyponym, it inherits the interface. So in other words, whenever you go through and you say implements list 61b, in the same way that if I have a license that says I'm a doctor, there's a lot you're going to expect from me, okay? Same deal. So the interface consists of all the method signatures, all the things you expect a doctor to be able to do. Prescribe drugs, like help you when you're sick, those kind of things. Okay? And actually, it turns out that these relationships can be multi-generational. That is, we can have, say, government official at the very top. Government officials should serve the people. Lower down, we may have mayor. So a mayor is a governmental official. So it does all the things that governmental officials share, serving people, but the mayor also has to do things like balance city budget or whatever that may mean. And then you may have specific mayors like LaGuardia or whatever. Okay? So in the diagrams that I'm going to have in the future, I'm going to specify that any interface is going to be in white and any class is in green. So you can think, if you want to use people as the example, these are job titles or categories of people, and these are going to be specific people. So interface inheritance is going to be just an incredibly useful tool for generalizing code. I think it's a really, really lovely idea in programming languages. And we've already seen it in action, in fact. If we look at our word utils class, it can handle any kind of list. And that's real nice. So given that fact, let's talk a little bit about implementation inheritance and how it interacts with the golden rule of equals. So there's a little bit of a paradox that a student some number of semesters ago was a little bit vexed about. I decided to roll it into lecture. Maybe it's not the most exciting thing, but I'm going to bring it up anyway. So the first fact is, whenever you say x equals y, or whenever you pass a parameter to a function, you're just copying the bits. Remember that. 2, remember we had this rule about type checking in Java, which is that a memory box can only hold 64-bit addresses for the appropriate type. So in other words, we can't say string x equals new dog. That's not allowed. However, if we look at this code, it actually seems like we're doing that. We're saying new A list, and we're storing it in an A list box, this A list memory box, and we're passing it into this box. We're copying the bits. So in other words, how did these bits, which are stored in an S list box or an A list box, how did those end up in a list 61b box? Well, let's actually, just for the sake of the argument, let's run this in the debugger and see exactly what I mean, in case you didn't quite follow that. So we look in the visualizer. When we get to this point in our code, we see that elk are watching, yada, yada, yada. And we step into this thing. So here's some list. It is a 64-bit memory box that holds the address of a list. And then whenever we go, we step in, we get here, we see a new variable is created called list, and it's of a different type, list61b. Yet these bits get copied here, but they're not quite the same type. So how is this resolved? Well, the answer is simple in Java. Java really thinks of an S list or an A list as a list, right? Same deal here with this example. An A list, it is a list 61b. So it makes perfect sense that a list 61b variable can hold the address here. In other words, you may be a Western doctor, an Eastern doctor, whatever tradition you may come from. But if there's a commonality about what things we expect from those doctors, then it's safe to be able to ask them to say, help us, okay? The results we get back may be different, but we can safely ask it and they won't get confused. Maybe that's the way to think about it. The jargony way of putting it is that if X is a superclass of Y, then memory boxes for the class X may contain Y. In other words, the list 61b, a list 61b variable can hold a reference to an S list, an A list, or indeed any list that could ever be. So let's see if that actually made sense to you. Okay, and this will be the rest of our kind of, tedious inheritance philosophy lecture. But consider this question, and maybe pause it here. Will this code compile? What do you think it'll do? And if so, what'll happen when it runs? And this is a bit of a test of your deep understanding of the golden rule of equals. So think about this, pause the video, and then I'll spoil it. Okay, I was assuming you were pausing, so I was giving you time to pause. All right, let's try running it. So in this file, I have the code commented out. Let's here exit this debugging session. Instead, let's run this. We will run is a demo. Okay, oops, debugger. All right, so when I run this code, we get up to this point. We'll actually show the visualizer, and we'll step over this. So we see that this first line, it compiled fine, first of all. We know that because there were no red squigglies. The answer is not A. And then how about this line? Well, it creates a new S list, and then it stores that address in some list. That's totally fine. And then what happens whenever we try and add first? Well, it turns out that this sum list pointer will actually be able to execute add first. So when I click this thing right here, it'll work just fine. Okay? So the answer is, in fact, D. Great. So that's a little bit more about the golden rule of equals, just making sure. I mean, these are things you might not think about really deeply and critically when you're learning how to program, but I figured I'd bring them up since, hey, you can always watch me at 1.5x or 2x speed.